So we've looked at some simple ionic compounds or binary ionic compounds between single metals and single nonmetals, gaining and losing electrons to form ionic compounds. And now we're going to look at some of the properties of these ionic compounds. First thing I want to look at is the crystalline structure of an ionic compound, because they vary greatly in terms, depending on the number of atoms in the compound and the relative size of the cation versus the anion. So the simplest structure we can see here is the sodium chloride on the left, which is this kind of just alternating. Every sodium positive ion is surrounded by negative chloride ions, and this kind of cubic structure. Below on the screen here we have a nickel arsenide, whereas we get a different kind of number of faces in that structure because of the way the edges are set up between the arsenic and the nickel ions. And on the right we have what's referred to as copper sulfate. So notice there are three elements there. The copper is the positive ion, and the negative ion is actually made up of the sulfur and the oxygen, or what is referred to as the sulfate ion. This is referred to as a polyatomic ion, where more than one atom makes up a particular charge. So the copper would be the positive charge, and the SO4 would be the negative charge. And the structure you see there is what's called a space-filling model, where kind of have these large bubbles representing both the atom and the electron cloud, and kind of how they would fill in three-dimensional space. So these are different crystal lattices that are going to have a different set of properties. One of the things we measure with a crystal lattice is what's called a coordination number. The coordination number is just the number of oppositely charged ions that surround any given ion. So we have this kind of cubic structure here, again, one that's represented by the sodium chloride crystalline structure. And the coordination number is just going to be counting how many negative ions surround each positive ion in this structure. And in this case, you're going to get 6 of those negative ions around every positive ion. So that would be the coordination number here. Here it is represented again to the left with just a single kind of unit of that coordination number. Here on the right, we have a completely different compound, and so we have a different arrangement of cations and anions and a different overall coordination number. And what you get out of these crystalline structures, these crystalline lattices, are kind of the properties of these particular compounds. And so when we think about that sodium chloride as having that kind of cubic structure, well, it turns out anytime you try to fracture a sodium chloride crystal, you end up with some form of cubes and or at least right angles on your fractures, because they have to fracture in between those ions. And so those three-dimensional crystalline structures at the atomic / ionic level actually have implications for the macroscopic structure of these particular elements. So these are both images of sodium chloride under a microscopic view, and again you can see those right angle fracture lines. And here we have a whole set of other ionic structures, which kind of as a side note, many of these ionic compounds are the same minerals that you will have investigated most likely in your middle school science classes. The mineral name typically is some kind of an ite, but not always, whereas the ionic name is going to be that cation, anion. So calcium fluoride up there at the top is referred to as fluorite. And fluorite has a three-dimensional crystalline structure that results when you fracture it along those lines with these little diamond shapes that calcium fluoride crystals often form. Again, our sodium chloride, which has typically 90-degree angles for its fractures, this is referred to as halite in the mineral form. And then calcium carbonate, again, this is another polyatomic ion. The CO3 makes up the negative, the calcium makes up the positive, and that's referred to as calcite. And you can kind of see that face there is a little bit more like a rhombus. You've got that kind of angled side rather than those 90-degree breaks. All, again, because these each have different crystal lattice structures with different coordination numbers. But this is kind of the list we want to go off for general properties of our ionic compounds. And the first is that ionic compounds are fairly strong. And one of the ways that you measure the strength of chemical bonds is by melting point. The more energy it takes to melt something, essentially what you're doing is you're breaking down the bonds between your representative particles. And so if you have really strong bonds, you're going to have really high melting points. Ionic bonds are usually pretty strong, so you get pretty decent melting points for ionic compounds. And because they have strong bonds and high melting points, ionic compounds are generally solids at room temperature, and they have what we call low volatility. Volatility is one of the ways to think about it is just how rapidly something evaporates. And so alcohol has a very high volatility, whereas ionic compounds, which are solids at room temperature, are going to have low volatility. Many ionic compounds are soluble in water, and when we get into our chemical reaction chapter, we'll talk about how to sort out which ones are and which ones aren't. But in general, ionic compounds are usually pretty soluble in water. When they dissolve in water, they break up into their ions. So the process of solvation actually produces ions in solution, and those ions can actually carry an electric charge or an electric current. And so you can actually conduct an electric current through a solution of an ionic compound or in its molten state. Of course, we can dissolve salt at room temperature in water, so it's a whole lot easier to get an electrolyte from dissolving in water than it is in its molten state because of those high boiling points. But either of those things will conduct an electric current. And so this is one of the reasons why you don't want to be in a swimming pool during an electrical storm. A swimming pool's got a lot of chloride ions in it that chlorine gets converted into. And so not to mention if you have hard water, you're going to have other minerals that are going to be dissolved in there and are going to ionize. And so that electric current's going to move pretty good through the water. And if you're in the water, it's also going to move through you. As a general rule, ionic compounds also make brittle solids, meaning they don't bend or shape very well. If you whack an ionic compound, you're going to break it into pieces. It's going to shatter. So brittle means breaks, doesn't bend.